Hello guys, this is Tiffany and today I'm going to talk about this project investigating soil variability in an urban farm. Let's start with a quick intro on urban agriculture. What is urban agriculture? Why are they important and why are we investigating soil variability? As its name suggests, urban agriculture refers to agricultural activities taking place in urban areas. It can take place in the form of a more extensive system as well as in a very intensive form such as vertical farms. Urban areas are often perceived as having fewer problems in food insecurity due to the abundance and variety of food available. However, studies have shown that this abundance does not guarantee equal food security. In fact, urban food insecurity often occurs in the form of bad physical accessibility, unsafe food, and fluctuating food prices. Urban agriculture can utilize space efficiently for food production. It also encourages organic production, which lowers pesticide use, while diversifying food production locations, spreading the risk of disruption to food supplies, thus offering a resilient solution towards food insecurity. Despite the benefits, the implementation of urban agriculture could be challenging due to unique circumstances presented by urban environments. A lot of urban farms utilize compost as the main soil amendment, which could lead to high salinity levels and excessive nutrient inputs. Urban soils are also more susceptible to contamination at a surface level, most notably from the combustion of fossil fuels by vehicles, while underground infrastructures can lead to deep soil contamination. Urban soils are thus highly variable, affecting its overall productivity. Our study took place at a local urban farm located at Camperdown, New South Wales, and their main challenges is the patchiness in growth, which has been observed consistently over multiple years. It is unclear what are the main causes. As shown in the picture, there is a low growth area near the walkway between two fields and an abnormally high growth around this area. In this study, we investigated the soil variation of the urban farm using electromagnetic induction techniques. EMI techniques are mainly applied in broad-acre precision agriculture for mapping purposes, yet it is unclear whether EMI techniques are applicable in urban agricultural settings. The image here is the EM38 sensor, and it is one of the most commonly used EMI tools in agriculture. And thus, the aim of the study is to understand the soil variation in a small intensive urban system to determine if EM38 can be used in an urban setting and to investigate the potential causes of growth anomalies observed on site. Now moving on to the methods. Our study can be divided into two sections. In the first section, we use the EM38 sensor. It measures the overall conductivity of soil, thus able to provide indirect information on soil salinity, texture, and moisture conditions. Both horizontal and vertical dipole mode was used for the study, and sampling was done in a triangular grid pattern. And for the second section, we took a total of 47 soil samples across the field to get data on soil's physical and chemical parameters. This table here summarizes tests run on soil samples. For data analysis, negative EM38 data was removed as it represents biased data caused by environmental interferences, whereas QGIS was used to create data and produce interpolation maps. Now moving on to the results. Interpolation maps of EM38 data showed that the apparent EC values are higher near the edges facing the street, while in proximity to metal infrastructures on the field. The areas of high apparent EC were highly associated with metal objects. The red lines in this image indicates metal structures, and it is clear that areas with red lines also have higher EC readings. Whereas for soil samples, a particle size analysis has suggested that the soils at the farm is sandy. The bar chart shows distribution of different particle sizes and the box plot suggests that soil particle sizes is fairly uniform across sites. Lab EC suggested that the soil is non-saline, ranging from 0.05 to 0.25 ds per meter, averaging at 0.11 decisiemens per meter. The interpolation map showed that EC distribution of the top field is higher on the top side, followed by a smooth low to high EC gradient. The bottom field showed a patchy distribution of EC values with higher values on the bottom right. pH distribution ranges from 5.9 to 7 with a mean of 6.3. The variation is lower on the top field and higher on the bottom field. Our results also suggested an undersupply of total nitrogen, with total nitrogen at 0.13%. The map here illustrates the distribution of nitrate and ammonium, which are forms of nitrogen readily available to plants. Both maps somewhat resemble the Lab EC map, especially the nitrate map. The ammonium map is slightly patchier. Phosphorus levels ranges from 56 to 157 mg per kg, averaging at 92.7 mg per kg, which is considered an oversupply. Potassium levels ranges from 70 to 437 milligrams per kilograms, averaging at 179.8 milligrams per kg, which is also considered an oversupply. Both phosphorus and potassium maps suggested patchy distribution of nutrient across the field. Moving on to data variability, there's a notable amount of variation across the dataset, with EM38 data having a significant amount of outliers. Other soil parameters presented smaller yet still considerably high variations across the dataset. In general, there is an undersupply of nitrogen, as well as an oversupply of potassium and phosphorus. Now moving on to the discussion. Regarding the high and low growth areas, it is not entirely clear what the true causes of growth anomalies are, but for the high growth area, it is located in the area of high phosphorus and of a more optimal potassium level. It is likely that the better nutrient balance have enabled better growth, but it doesn't fully explain why the high growth region stayed in a perfectly diagonal strip over multiple years. As for the low growth area, it is more likely due to competition with neighboring grapevines for moisture, as well as non-soil factors such as sun exposure. A more wildly guess for the cause of the high growth region is the leaking from water pipes underground, which provides extra moisture to support higher crop productivity. But in such case, the MM38 interpolation map should reflect higher values at the high growth region. Unless there is further information on the underground infrastructures or provided with non-biased EM38 readings, the cause remains unclear. The Lab EC interpolation maps mainly reflect the areas where metal structures were located. Even with dedicated data processing, the maps still strongly indicate metal presence, suggesting that the lower limit of apparent electrical conductivity acceptable for the farm should be increased to counter the effects of metal interference. In addition to the metal, there were also other interferences such as overhead power lines and potentially underground infrastructures, suggesting that more work needs to be done in order to find out the most effective threshold in removing biased data. Further investigation would be required to understand the dynamics of urban structures within the farm. To conclude, EM38 is not applicable in our study site due to frequent interferences from urban infrastructures. Unless a threshold is developed for filtering non-biased EM38 data, the resulting interpolation maps will not be able to faithfully reflect the soil conductivity of the farm. A more faithful reflection of soil conductivity will give us better insight into soil moisture distribution and its potential influence on crop productivity. For future studies, we should focus on areas of growth anomalies to gain a better insight of the observation and hopefully utilize the knowledge to boost overall farm productivity. This is the end of the presentation, and thank you for listening.